Okay, so for video two, I'm going to go through the Kaggle dataset. Um, so at first, I'm just going to go through some general data exploration. Then we're going to go through the specific questions that we had to answer, and then we'll get back into the Kaggle dataset. So when I first looked at the database, I decided that I kind of wanted to split it up for exploration. So I split it into qualitative variables, all the factor variables, a data frame of quantitative variables that seemed normally distributed, and then a data frame of quantitative variables that seemed like they were heavily right skewed. Um, this is the data frame that had all the normally distributed quantitative variables. This was our correlation plot. You can see that there does seem to be a lot of multiple collinearity issues that may be arising between the independent variables. But it does look like our dependent variable sale price has a lot of good correlations with a lot of these independent variables. Um, so I decided to take a closer look at each of these relationships. And pretty much I split it into, every four columns, and then I added sale price. And this gives me the scatter plots, and it shows me the relationship between the two. You can see that a lot of these relationships are pretty significant and pretty high, but you can also see that there's some collinearity issues. Like garage cars has a 0.88 correlation with garage area. That's something that needs to be addressed. So when I plugged all these things in into the VIF chart, I saw um, uh, that it doesn't look terrible, but anything above five would be considered bad. But it's okay. It's not terrible, but it still gave me concern, and I decided I wanted to start dropping variables. Um, so these are all the variables they ended up dropping, and now we're left with a correlation matrix that kind of looks like this, and we can see the relationships over here. Uh, and now when we look at the VIF chart, none of them are over uh, 2. It looks much cleaner. I don't know if by hand selecting and doing it this way, if I drop variables I shouldn't have. I mean, I didn't really know which way to go, and I figured with 70 different independent variables, I needed to try and cut them down a little bit. So now that we're done looking at the normally distributed ones, let's look at the right skewed variables. Now, the relationships here between sale price and the right skewed don't seem as strong. You can see that here as well. And you can see that a lot of these are heavily zero inflated. And I kind of thought to myself, well, how can I suss out these relationships if I take out those zeros? In other words, like what would it look like without those zeros? So my first idea was, okay, well, let me try and log transform and see if that will somehow make the zeros not as important. And the log transformation, obviously, it did not work. Um, so then I thought to myself, okay, well, what if I just tried to look at the scatter plot of my sale price against these things when I filtered out all occurrences of zero. And here now you can see that we can see pretty clear linear relationships between, well, for instance, this variable of basement square footage and sale price. Here we can see that number 2, it does not have a strong relationship at all. Versus if we went back and we looked at our original matrix, original plots for these, uh, like this, you can tell that. Sorry, this one. It doesn't. This plot does not look as strong as the plot that without the zeros. Like this clearly, I don't know, just seems stronger to me. Um, so pretty much I used this to hand select several of these relationships that look like they were strong and filter out all these weak ones like the one here, which happens here. And this leaves us with this 4 different variables to choose from. And um, So from there, I decided let's put this all together, our normal, our right distributed, and what do our relationships look like. And this is a plot of our relationships. And here's everything so far to date. We haven't looked at any categorical data, but we've kind of looked at all the numeric data. And I've hand selected, which variables that I kind of think I want to plug into a model. So moving away from the the Kaggle work and onto the more specific questions that were asked of us to be done with the Kaggle set. So we were asked to make a correlation matrix between two different dependent variables and sorry, two different independent variables and our dependent variable, sale price. So I chose lot frontage and garage area. So you can see that sale price and lot frontage have 0.35 correlation, which if we went back up and looked at our scatter plots, we would have seen. So from here, we were asked to look at each of these relationships and create a confidence interval based on an 80% for that relationship. So what we discover is that at 80% confidence interval for this relationship pretty clearly show that there is in fact that these variables are not independent and they are actually dependent upon each other, and for all three of these. So our mean, our confidence interval here ranges nowhere near zero. It never. So it's from 0.31 to 0.38, from 0.60 to 0.64, and from 0.31 to 0.37. So further, we were asked, should we worry about family-wise error? And I would think in this case the answer to that is no, because you'd worry about family-wise error when your confidence interval is showing something that's much closer to zero, when your p-value is much lower, because the chances of something with a p-value of zero point zero 0.03 being considered to well, considering 0.03 considering us to reject the null, it could be that we're falsely rejecting the null. But in this case, it's very unlikely that we are falsely rejecting a null. For an extra test, I decided to uh, create a confidence interval for something that I knew from before was actually independent of each other. And we can see that from that test, these two variables actually do cross zero, and it would show us that they are not dependent upon each other. So our next question was to create a 3 by 3 correlation matrix and to invert that, which is done with the solve function, and giving you a precision matrix, which I guess was also called a value inflation matrix. We were then asked to multiply our correlation matrix by the precision matrix and the precision matrix by the correlation matrix, and to do LU decomposition, which was all done functionally. I decided to try and I've actually already got into the VIF, but being that this has something to do with VIF, I looked into VIF here and plugged it in and created a VIF function just because we were messing around with these types of things. From there, we go on to the calculus-based questions. So the calculus-based question pretty much said that it wanted us to fit a exponential function to the exponential distribution to match what our where some random variable that we were looking at for a right skewed variable. What I actually found though was that while the exponential function does an okay job of mimicking the variable I chose, that the negative binomials seem to do a much better job. I think that's because it's just very zero inflated, but that's weird because I thought negative binomial was meant for count data, and this isn't count data, at least not the variable I chose. But you can actually see that. I ran a test. I found a way to, through Broom glance, to run a test, and you can see that the ASC and BSC levels, minimizing that would mean that the fit is better. So it's saying that the fit of the negative binomial seems to be pretty significantly better than the exponential. But whatever, that's superfluous. That's not what was asked. So we fit the exponential, and we grabbed the theta, and we found that it's a 0.021. So now from here we were asked, from here we were asked to find the 5th and 95th percentiles using the CDF for the exponential. And the way you solve for that is just simply you take the log of 1 minus whatever probability you're looking for divided by negative lambda. So at the same time, so that comes out to this, and then at the same time, I went in and we were asked to compare it to what the actuality is for this variable that we chose. So I went in and I looked at the open porch. I grabbed the quantiles, and it prints out to here. And you can see that in actuality, because it's very zero inflated, the lower bound is 0 and the upper bound is 175. And for the sim, the lower bound is 2.39 and the upper bound is 139. So the exponential does a decent job, but I mean, I wouldn't say it did an excellent job of kind of giving us an estimation. Um, from here, we were also asked to just custom build a confidence interval, and that's just pretty simple. I just took the mean of our vector, and I found the standard error, and I just did minus the error from the mean to get the upper and the lower, and boom, prints out that we have our upper is 50 and our lower is 43.612, and our mean I think was 46. I don't have it printed here. Okay, so that was it for all those specific questions. Now we're getting back to Kaggle. And so in the Kaggle data set, I decided, okay, well, let me look at the factor columns, and I have this custom function which kind of prints out like what percentages of each factor is of the whole. It gives you a good idea of seeing how often values occur. And then from there, I decided, well, let me plot out all of the factors. And the way I thought about it was, I want to get rid of some of these. So the ones I want to keep, I thought to myself, well, I want to see if there's somewhat of a difference between each factor level, and I want to see kind of a narrow range of results. Um, and I guess in my mind, I thought that would mean that it would give us values that are important towards predicting sale price. But none of this really takes the correlations into account. So perhaps this hand selection I did wasn't necessarily a correct method. But anyway, after it's all said and done, I eliminated a whole bunch of those columns. Um, like landscape, roof style, exterior quality, condition. I kept strong predictors, which were like overall quality, which looked very strong. Um, so next, right before I get into modeling, I had to address the problem that there were several NAs in our data frame. So I just imputed using, I think I used a random forest, and I have that all commented out because obviously that takes a while to print. But I ran the random forest, I saved the files, and they're actually loaded at the beginning of our data set, uh, right from the start. Yes. Or maybe it's in a hidden. I don't see it here. So perhaps I actually echoed equal false. But anyway, so I loaded in with all my packages. Yes, that's where it is, because with the packages, and the packages aren't here. So I loaded in these imputed data frames so that you don't have to keep running this. But as you can see, the mice package over here does a pretty good job of showing you, how where your variables are having any values, and and how bad they are. But from here, it's about running models. So I pretty much broke it into two things. I had these hand-selected model, which was me going through this entire data set and picking out what I thought was good. And for that, I had model one, which is just all of those plugged into a linear model. And then for model two, it was those with backward selection and then plugged into the model. And then for model six, I took all of those and I actually plugged into a grid search on ElasticNet. So the other data set that I used was pretty much just everything. Pretty much every single column that we were given, I decided to just throw it in. I had to actually take out several columns because the LM function wasn't running because of collinearity issues. Um, but other than that, I think there was 68 out of 71 or so of the columns were used. So this, just like before, this was used in an all variables model. This was a backward selected all variables model, and then an elastic net all variables model. So we run the models, and what I found was that my models performed okay. 0.86 r squared, 0.87 adjusted r squared. F statistic 80.1. Um, And you'll see I actually have the RMSEs printed out in a little bit. So this is my other hand selected with backward selection. Actually, the F statistic went up a little bit. Um, and then I go on to the full DF models, and these seem to run better. So like these where I did no data analysis, I just, just let the computer do its work. And what we got from this was a better result actually than what I, spent hours upon doing. And you can actually see here that I put what I did was being that the Calgo wanted to make a logged RMSE, I created their customary log RMSE. Um, Now, this wasn't cross-validated. This was just on a simple, train split. But what we found was that my two models that were hand-selected had about a 0.142, and the two models with literally everything in it performed better. And in the end, I'm going to end up picking this Model 3 over here as our function to run on. But I want to try ElasticNet. But ElasticNet was a pain because the idea that all your factor variables have to be created into dummy variables. So I had to, but model.matrix, I believe, handled this well. So I plugged it all in. I turned these all into dummy variables. So now we have, hundreds of columns. And from the hundreds of columns, I tried to fit this. Using the method that I found on this website over here, and pretty much it uses lambda levels that will show us that does Ridge fit better, does Lasso fit better, or is it better with ElasticNet. Um, so the results from this were not that good actually. So this is actually I think our mean squared error. This wasn't our the same as what we're comparing to above. When we ended up comparing these results to the ones above, I think it was significantly worse, although I could be wrong. But anyway, either way, it was worse, even if this was actually the root mean squared logged error, which I do not believe. Square root mean, okay, so this is the square root mean squared error. But as you can see, the best result we found in this was at 0.18, and the best result we found in this one was at 0.155, both of which would indicate that I believe Ridge alpha, because that alpha 0, which is Ridge. So both of those are using Ridge, but both are still worse than any of the results we had before. So ElasticNet really didn't help. So I decided, whatever, for the Kaggle project, let's go, let's predict. And I just plugged in the model with pretty much all of the variables in it that was not backward selected, and I used that to predict. I had to impute the data set for Kaggle a little bit, but when all is said and done, we make our prediction and we hand in our prediction, and I don't have Kaggle housing data. Hopefully I can get to this now, because I actually did this on my computer. So leaderboard. This might take a little bit. Wish I knew what my login was. Well, while that is loading, I believe it comes out to about 0.16. So just to show, I mean, I thought about, exploring and kind of doing some log transformations and adding some interaction effects. And in the end, I didn't do any of that. It was, it was too much. And then I actually tried to do a numeric only model, figuring, okay, well, maybe if I run a numeric only model, I can do some interaction effects between them and see how that runs. But the numeric models, its R squared was lower. I think its predictive power was lower. So I didn't go with that either. I even tried to plug in those numeric models into the elastic net. And even here, you can see the mean squared error was once again worse. So, I mean, there was no getting better results, but here I am with my submitted results at 0.16812 submitted 2 days ago onto the data set. And that was it.